Hello, this is Mario from ODEON. In this video, we will explain the calculation principles used for simulations in ODEON. An ODEON model will have sources and receivers defined by the user. Through methods we will explain in more detail later in this video, ODEON generates image sources representing specular reflections and secondary sources which model scattering. An energy histogram in time is constructed with energy contributions from the user-defined sources, image sources, and secondary sources. The strength of contributions is determined taking into account the directivity of the source, the absorption of reflecting surfaces, and the air absorption, which depends on the length of the reflection path. Additionally, these factors are all frequency dependent. From the energy histogram, the squared impulse response is produced. Then, using backwards integration, we can derive the decay curve, and from it, the acoustic parameters. Due to the frequency-dependent factors, this procedure is done separately for each octave band. Depending on the reflection order, that is, the number of reflections on a single ray, ODEON will distinguish between two types of reflections: early reflections and late reflections. The reflection order at which ODEON makes the distinction between the two types is called the transition order. In this example, the transition order would be 2, though it can be freely defined in the setup. Early reflections add strong contributions and are quite deterministic, while late reflections have lower energy and more randomness. So, ODEON uses different calculation methods for early reflections versus late reflections. The distinction of early versus late reflections in ODEON applies specifically when using point sources. For specular early reflections, ODEON uses the image source method. An image source is a representation of specular reflection using a mirror image of the source relative to the reflection surface. Diagrams throughout this video will be two-dimensional. But keep in mind that these represent three-dimensional phenomena. The image source is able to represent reflections for rays hitting any point of the surface. There can also be image sources for sequences of multiple reflections. For example, here, S12 is an image source for a reflection that hits surface 1 and then surface 2. In the same way, we can also find an image source S21. So, every image source is associated to an original source, a series of surfaces, and a reflection order. However, the image source method originally requires all possible combinations of surface reflections up to a certain order. In our case, up to the transition order. The number of image sources would grow exponentially. Therefore, with a high number of surfaces, this generates a huge amount of image sources. This example is for only 8 surfaces, but a realistic project can have hundreds of surfaces. With just a transition order of 2 and only 100 surfaces, this results in 10,000 image sources, and many of these image sources will be invalid to begin with. This can be because of surfaces that are unreachable from the source within the transition order, or because they are too small and are unlikely to be hit by a finite number of rays. So, ODEON first uses specular ray tracing up to the transition order to identify which surfaces are relevant for the current source position. This greatly simplifies the number of image sources, and consequently the number of calculations, by discarding irrelevant surfaces from the beginning. Finally, an image source is considered visible when the reflection path can be backtraced specularly from the receiver, starting at the direction of arrival and without hitting any surfaces outside of the original reflection sequence. Since we are starting from the receiver, we should follow the surface sequence from last to first. In this example, let's look at which sources are visible. For starters, the original source is visible from the receiver, meaning we have a contribution of direct sound. For image source S1, we will emit a ray from the receiver and it should hit surface 1. It indeed does, and it arrives back to the source, making it a visible source. For image source S12, it should hit surfaces 2, then 1, then arrive to the source, in order for it to be visible. But when backtracing, it first hits surface 1 instead. Therefore, this source is not visible. An image source being not visible basically means that the reflection path is impossible with the current geometry and source and receiver positions. So, in this case, it means that it is geometrically impossible to establish the sequence of source, surface 1, surface 2, and receiver, using only specular reflections. When backtracing to S2, it hits surface 3, therefore it is also not visible. However, for S21, the ray hits surface 1, then 2, and arrives at the source. Therefore, S21 is visible. Finally, when emitting a ray to S4, it hits surface 6 instead, making this image source not visible. Image sources found to be visible add energy to the energy histogram, from which the squared impulse response will be produced later. Keep in mind that these contributions take into account the source directivity and the absorption of surfaces and air. For early scattering, ODEON generates early secondary sources on each surface associated to a visible image source. The combined energy of the secondary sources is according to the reflection-based scattering coefficient, which combines scattering due to surface roughness and scattering due to diffraction, and the remainder of the energy is kept by the original image source. We explain calculation of scattering in more detail in our video on the reflection-based scattering method. Additionally, the secondary sources will have Lambert directivity. Then, each early secondary source emits rays, referred to as early scatter rays. These reflect from the current reflection order up to the transition order. This means that if we have a transition order of 3, and the early secondary source was created at the first reflection, the early scatter rays will only reflect for the 2 remaining reflection orders. And for early secondary sources created at the second reflection, early scatter rays will only reflect once. At the reflection points of these early scatter rays, another single secondary source is created. Finally, all early secondary sources directly visible from the receiver add a contribution to the energy histogram. The image source method and early scattering method are only used up to the transition order for a couple of reasons. The first is that at higher reflection orders, the number of calculations grows exponentially. And the second is that specular energy becomes less important at higher reflection orders. Therefore, after the transition order, ODEON uses a different method that's more efficient and more focused on scattered energy. This would be the ray radiosity method, which is a modified version of ray tracing. In classic ray tracing, a detection sphere would be defined around the receiver, and the ray would be added as a contribution when it intersected this detection sphere. However, the definition of this detection sphere is quite arbitrary and presents problems whether it is too big or too small. Therefore, ODEON uses a different approach. Ray radiosity consists of 2 phases: rendering and gathering. In the rendering phase, rays are emitted from the source, and the reflections are calculated according to the vector-based scattering method. This is a weighted vector sum of specular and diffuse reflection, which are both determined by the reflection-based scattering coefficient. Again, keep in mind that this diagram represents a 3D principle. Therefore, the zone of probability would actually be the surface of a sphere. For each ray, no additional action is taken up to the transition order, since early reflections have already been calculated by the previous methods. But after the transition order, each reflection point will generate a late secondary source, which again will have Lambert directivity. This continues up to a time limit called the impulse response length, and then repeated for a number of late rays. Both parameters can be defined by the user in the room setup. One should keep in mind that many late secondary sources will be created even with few late rays, so it doesn't require a really high setting to obtain a good energy decay. For standard rooms, 1000 late rays is typically sufficient. In the gathering phase, a check is performed to determine which late secondary sources are directly visible from the receiver. Visible secondary sources add a contribution to the energy histogram. Since the rendering phase is receiver independent, another advantage is that the positions of late secondary sources for an original source can be saved and used for any receiver. So, when calculating for several receivers, only the gathering phase is repeated. Together, the image source method, early scattering method, and ray radiosity method make up the full energy histogram. And the squared impulse response can finally be produced. We should keep in mind that the transition from early to late methods depends on the reflection order and not on time, and that reflections will happen at slightly different times due to different path lengths. Therefore, in time, there will be a gradual shift from the accurate early methods to the efficient late methods. For line sources and multi-surface sources, all calculations are done with the ray radiosity method, so there is no distinction between early and late reflections. While the energy histogram is only used internally for calculations, ODEON is also able to produce a reflectogram and 3D reflection paths as a calculation result in Editions, Auditorium, and Combined. However, they are based on image sources, meaning they can only be produced when using point sources, they will only show reflections up to the transition order, and will not include early scattering. To see higher reflection orders in these results, the transition order can be increased in the room setup. Generally though, we recommend the default value of 2. ODEON is also able to calculate diffraction paths around surfaces, up to 2 points. In the first 3 figures, a diffraction path is established successfully. However, in the last figure, the diffraction path would require 3 points, and therefore does not get established. Rather than emitting one ray after another, it is also possible to calculate small packets of acoustic energy emitted simultaneously. This is called particle tracing, and it can be visualized in ODEON in the form of 3D billiards. The energy and propagation angle of each particle is adjusted at each reflection, according to the absorption and scattering of the surface. Aside from producing informative visualizations, particle tracing also allows us to derive global decay curves, and consequently global reverberation times for the room, which are receiver independent. If you are interested in average reverberation for the whole room, these global estimates are more reliable than statistical formulas like Sabine, since the global estimates do take into account the geometry of the room via the particle tracing. However, keep in mind that parameters such as reverberation time will vary at different positions. So, you might still want to use point responses for projects and for comparing against measurements. 3D Billiard and Global Estimate are available in Editions Industrial, Auditorium, and Combined. While these methods are the basis of calculations in ODEON, there are finer details to the algorithm that we periodically fine-tune to enhance calculation speed and accuracy. The calculation methods we have described in this video are referred to as energy-based methods. This is because they only keep track of the energy of the rays, without taking into account phase information. This means that phenomena based on phase and interference, such as resonant modes, will not be calculated. For this reason, ODEON is mainly recommended for situations where resonant modes are not highly dominating, such as in medium to large size rooms. Small rooms will have strong resonant modes at low frequencies, so ODEON might not be able to provide accurate results at the lowest octave bands in small rooms. Results at medium and high frequencies might still be reliable even in small rooms. A good rule of thumb you can use to know whether you can calculate a room's acoustics in ODEON is the Schroeder frequency. For a given room, this is a theoretical minimum frequency at which there is enough modal overlap that energy-based methods can be applied. In other words, this gives you the lowest frequency you can reliably calculate in ODEON for a specific room, though you could still go a bit lower. This is explained in section 9.1 of our user manual, which you will find in the Help menu, User Manual. You can also find it in our website odeon.dk, Downloads, User Manual. That concludes this video, and we hope you have found it useful.